Okay, now let's go over some short answer, multiple choice portion of the exam. Question here is asking us a gas that goes into a solid. A gas to a solid, the change in entropy is, what do you guys think? We have a gas going into a solid. All right, so entropy is delta S. This is a measure of disorder. Okay, so what is the most disordered state of matter? Okay, so this S can be standalone or change in S, and the most disordered state of matter would be a gas. Okay. They move around a lot. They take up a lot of space. Next, most disordered would be the entropy of a liquid, and then an entropy of a solid. So solid is very, very ordered, right? So one thing I want you to know about entropy, not only is it related to disorder, this is a part of thermodynamics, but a couple of things lead to an increase in entropy or disorder. Okay, one of them is increasing the temperature. This should make sense. If you increase the temperature, there's more motion, there's more collisions. You know, entropy is all about motion. Okay, a solid doesn't have a lot of motion. A gas has a lot of motion, right? Okay. I'm talking about it from a molecular standpoint. So we're looking at more motion, more mass, all of these things, and an increased temperature give rise to an increased entropy. Okay. So having said that, this is one part of thermo. Okay, what we learned here in thermodynamics, there's whether a reaction is going to be energetically favorable. It's going to have an entropy component. It's going to have an enthalpy component. And really, the final judge is delta G. This is called Gibbs free energy. This is the energy that is capable to do work. Okay, Gibbs free energy. So this is all thermodynamics. Let's go back to this question. A gas that goes into a solid, the change of entropy. Oh, what do you guys think? What about signs? Okay, one thing I forgot. So we associate more disorder with positivity. Okay, more motion, more mass. Okay, all those things will give rise to a positive number of entropy, positive value, and a negative number for something that's more ordered. So the answer here, a gas going to a solid, do you guys agree with me that it's negative? Yes or no? Yes, okay, right. A gas going to a solid. Okay, this is negative. Right, this delta, yeah. Okay. All right, let's talk about a battery here. Okay, a battery is another way of calling a galvanic cell. And a galvanic cell has two components. Okay, we have an anode couple. Okay, and they're separated by what's called a salt bridge. Okay, a salt bridge. A salt bridge is two lines, and then a cathode couple. A galvanic cell is kind of like a battery. We're using chemicals to create a battery. This is electrochemistry. And so those are the two parts of a battery or a galvanic cell. Type of reaction. Okay, the type of reaction that happens in a galvanic cell is called a redox reaction. A redox reaction. And a redox reaction is an exchange of electrons. Okay, we are exchanging electrons. So let's take our example here with Marina. Okay. I give an electron. Okay, I give an electron. if I give an electron, I become positive. Okay. We'll call this a one electron transfer reaction. Okay. Somebody has to take the electrons. Somebody has to take an electron. Okay. So, oh man. Bad. Okay, so for every giver of an electron, there is a taker. Okay. So the idea is, the whole idea behind this activity series, okay, which is something you should bring on the exam. Let's say there's Marina, Eric, you, Maria, and you, Bailey. Okay, I give this one electron. This is a one electron transfer reaction. Who's going to take it? It's a competition. You may be better at taking that electron. You may be better. You may be better. Turns out she's the best. And then you're second, you're third, you're fourth. Okay, so that's the whole idea behind what can oxidize something. Okay? So back to this. Okay, I give an electron. Let's say Marina here takes it. Okay, we are a redox couple. We are a couple. She takes it. Remember, this is a one electron transfer reaction. So she takes that electron. She becomes negative. Okay, negative. All right, so in this one electron transfer reaction, okay, this and electrons cancel. We don't want free electrons anywhere. So we get VJ plus Marina, myself plus Marina. I give up an electron, so I become positive. She takes that electron, and she becomes negative. Okay, so in this aspect of a redox reaction, somebody gets oxidized, and somebody gets reduced. Okay, who gets reduced? Okay, so who gets reduced is whoever gains the electron. Okay, so you notice all of these are gaining electrons. Okay, so that's the person that gets reduced. So who gets reduced here? Okay, it's going to be our classmate Marina. She gets reduced because she gained that one electron. Who gets oxidized? It's the person who loses the electron or the chemical. In this case, I gave away an electron. I lost an electron, so I get oxidized. All right, coming back to a battery. In a battery or a galvanic cell, there's two components here. Excuse me. One of them is called the anode. The other one is called the cathode. Okay, so if we were a battery, okay, what role will I play? Will I be the anode or the cathode? So here we got to remember red cat eats an ox. Can we remember this? Red cat eats an ox. Okay, reduction occurs where? Cathode. Oxidation occurs where? Anode. Okay? So coming back to this question, okay? Oxidation occurs where? In the anode. Okay, 'cause I may switch these in the exam and say reduction occurs where? Then you'll write cathode. Okay? So oxidized and ox, I am getting oxidized. If we are going to be a battery, I would be the anode. Red cat, a cathode is where you gain an electron. You notice all of these are gaining an electron. So these are reductions. These are reductions. So she would be the cathode. Okay. And this is the answer. All right, let me just tell you this. I get oxidized and Marina gets reduced. Can we agree upon this? Marina gets reduced. I get oxidized. So I am the agent that causes her reduction. I am the agent. I am the person that causes her to get reduced. So I am the reducing agent. It's backwards. That's why it can be confusing. Okay? I myself am the reducing agent. All right, let's look at Marina. She gets reduced. She is the agent that causes my oxidation. She, by getting reduced, caused my oxidation. So she is the oxidizing agent. Okay, so make sure you're good for short answer portion, multiple choice portion, no calculations, this type of terminology. Okay, what happens where? All right, let's move on to number 3 here. For the for the reduction half reaction, for the reduction half reaction that's shown here, okay, the E reduced for the following reaction, it looks like if you look from this reaction to this reaction, what did the person do? He took this and multiplied it by 3. He took this and multiplied it by 3. So he took this half reaction and multiplied it by 3. So what will the number be? The same. Okay, this is a very important point. All these numbers stay the same. What's the only thing that can change? The sign. The positive, negative can change, but these numbers will never, never, ever change. So what's the answer to this question? It's going to be 2.87. It's what we read out from the table here. Okay, so these numbers will never change. Okay, the only thing that will change is the positive, negative sign. All right, that's the important point here, talking about this sheet. All right, for a reaction to be spontaneous, what will E cell be? This is standard state. Okay, spontaneous. So when we're talking about spontaneous, we're talking about a reaction that favors the products. Okay, spontaneous. It just happens on its own. Okay, reactions that happen on its own are spontaneous. Reactions that do not happen on their own are called, guess, non-spontaneous. So for a reaction to be spontaneous, all 3 conditions must happen. One of them is that you have a positive voltage. We go to Walmart to buy 9-volt batteries, 12-volt batteries. Okay, not negative 9 volts or negative 12 volts. Okay, if we're talking about in terms of equilibrium, the equilibrium constant will be greater than 1. Okay, greater than 1. All right, remember, this is products over reactants, no solids, no liquids. Products over reactants, no solids, no liquids. And then finally, the delta G, this is Gibbs free energy, it's going to be negative. Okay, so all these 3 must happen, and then we say they favor the products. This delta G negative, Gibbs free energy negative, is called an exergonic reaction. In other words, it releases free energy. So you ever take a biochemistry class or a biological chemistry class, if delta G is negative, that means it can, that released energy can, move a muscle or do something, okay, move the cell or whatever. Okay. Okay, it's just energy that can do work. All right, so all these 3 things must occur for a reaction to be spontaneous, and by spontaneous we mean it favors the products. So what's the answer to this question? For a reaction to be spontaneous, E cell will be what? Positive, negative? Depend on the temperature. We'll have a K less than 1. What do you guys think? It will be positive voltage. Okay, positive voltage. That's the only way you can get a electrochemical reaction. The only way you can get a redox reaction to go to the product side. All right, here we go. Okay, if K is positive, this is called the equilibrium constant. Okay, we do not put solids, we do not put liquids in here. And just a lot of people miss this on the exam. This is unitless. E cell is positive, then the reaction will be, we went over this, then the reaction will proceed to the positive side, or to the product side. All right, we talked about this in question number 6 with Marina. A reducing agent is a substance that gets oxidized. She is the agent that caused my oxidation, right? No, she is the agent that caused my oxidation. So, now I'm getting confused with the backwardness. A reducing agent. So, a reducing agent is the agent that caused my oxidation, right? So the reducing agent becomes oxidized. Reducing agent. Yeah. Yes, I am the agent that caused her reduction. I get oxidized. Okay. Did I confuse everyone in the room? All right, so it goes backwards. The reducing agent is the substance that gets oxidized. Okay, I get oxidized, but I am the agent that causes Marina's reduction. So I am the reducing agent. Henceforth, the reducing agent becomes oxidized. Okay. All right, so I'll have these available for the exam. I printed out a whole bunch, but some true-false questions for us here. How do we read this? Okay, anybody remember how we read this? All right, I highlighted one here. Okay, so anything below it can get oxidized. Okay, anything below it can get oxidized. Anything above this remains reduced, and you take the one and you flip it to get it oxidized. These are the only two ways that you can get a positive voltage. Okay, let's go over this one more time. What are the two ways you can get a positive voltage? You pick any one of these half reactions. Okay, and these are all reduction half reactions. You pick any one. Anything below it can get flipped. Anything below it can get flipped. Okay? In other words, iron plus 2 can oxidize chromium to Cr plus 3. Iron plus 2 can oxidize zinc to zinc plus 2. Iron plus 2 can oxidize manganese to manganese plus 2. Iron plus 2 can oxidize magnesium to magnesium plus 2. Iron plus 2 can oxidize sodium to sodium plus. Okay, that's one scenario in which you can get a positive voltage. Okay, the other scenario is this. Okay, let's look back at the highlighted reaction. Okay, iron can reduce Cd plus 2 to Cd. Okay, iron. Okay, so in the process, this gets flipped. Keep everything above the same. You flip the one that you choose. Okay, that's for if it's above. Okay? If it's above it, keep everything above it the same. You flip the one you choose. That's the second way you can get a positive voltage. Okay? So anything below it, flip it. Anything above it, keep the same. The one you choose, flip it. Okay? Those are the two ways you can get a positive voltage. So having said that, let's look at this here. All right, let's see here. Beryllium plus 2, so you got to be careful. These are a little tricky. Will cause the reduction of Al plus 3 to Al. Beryllium plus 2 will cause the oxidation of Al plus 3 to Al. Will cause the oxidation. Yes, this is false. This is false. Right? Beryllium plus 2 will cause the reduction. This is true. This is true. Beryllium plus 2 will cause the reduction. Why is it true, Lately?
Because Al3 is above.
It's above, yes. So is it true or false? It's true. Okay. Did you catch yourself?
Yeah.
Okay, thank you. The answer to this is true. Alright, so just be careful, that's all. Na plus will cause the oxidation of Br minus to Br2. Na plus will cause the oxidation of Br minus to Br2. So where's Na plus? Here's Na plus. Will cause the oxidation of no, it will not. Br minus to Br2, it will not. What will it oxidize? It will oxidize calcium, it will oxidize strontium, Sr, it will oxidize barium, it will oxidize K, potassium, it will oxidize lithium. Do you see Br anywhere there? So the answer here is false. Okay, zinc solid will cause the reduction of cadmium plus 2 to cadmium solid. Zinc. Okay, where is zinc here? Okay, here is zinc. Will cause the reduction. So, reduction of cadmium plus 2 to cadmium solid. What do you guys think? True or false? So it's saying zinc. Oh my gosh. Okay, it's saying zinc will cause the reduction of cadmium plus 2 to cadmium solid. Is this true or false? I think it's true, yes. Because zinc plus 2 will cause the reduction of this. It will cause the reduction of everything above it. Yeah, it's true. All right, let's move on to the next one here. Lithium is most likely to get reduced in the standard reduction potential table. Lithium is most likely to get reduced. What do you guys think? Li plus, not Li, Li plus. Most likely to get reduced. True or false? Li plus. Would this like to get reduced to lithium? Negative 3.05 volts. Okay, what would likely to happen? What would more likely is favorable is lithium gets oxidized to Li plus, losing that electron, giving you positive 3.05 volts. So lithium plus reduced to lithium solid is not likely to happen. Negative 3.05 volts. Lithium is most likely to get reduced. No. Okay. Here, lithium getting reduced gives you minus 3.05 voltage potential. Not likely to happen. What is likely to happen? Lithium solid losing the electron, giving you Li plus. So if you agree with me, I'm calling this false. What would be true is that lithium solid is more likely to get oxidized. All right, are there any questions or comments before we do one more, and then we have about 3 computation problems? Then I think we're done. 4? Anyways, we have some math problems. Which is a stronger oxidizing agent, Fe plus 3 at 0.77 volts or copper plus 2 at positive 0.15 volts? So the thing you need to remember is that the oxidizing agent is the one that gets reduced. And what do we know about things that get reduced? All of these are reduction or reduced. And the more positive it is, the more likely it's favoring the product side. Okay, so here you can see it right here. Okay, increasing strength as an oxidizing agent. Okay, so we're looking at things that are getting more and more and more positive. Right, so which is a stronger oxidizing agent? Okay, it's going to be the one that's more positive. Okay, more positive. All right, let's do some practice problems here. All right, so we have the galvanic cell notation. For the following reaction, calculate E cell, determine if the reaction is spontaneous or non-spontaneous. For spontaneity, we're looking for a positive voltage. All right, so this is how you do the thing here. Okay. So you have chromium solid goes to Cr plus 3. Okay, how many electrons and where should they go? Okay, does everyone agree with me? There should be 3 electrons on the product side to balance out the charge. Okay, plus 0 here, plus 3, minus 3 there. So this is an anode oxidation. Okay, that's what's happening in the blue. What is the voltage associated with this? Where are you? Here we go. Okay, you guys see that, where my pen is at? Okay, but are we going to write minus 0.74 volts? What will we write? Okay, we're going to write positive. Why positive? Why did we switch the sign? Because that's what's happening in our problem. So this is positive 0.74 volts. This is the E anode. All right, let's do this in purple here. We have nickel plus 2 goes to nickel solid. All right, nickel plus 2 goes to nickel solid. And then how many electrons and where? Do you guys agree this is 2 electrons on the reactant side? This is the cathode, because in the cathode we gain electrons. We also get reduced. And what's the voltage for this one? Can we look it up? What do you see here? I'm seeing negative 0.25 volts. We're going to keep it the same. Negative 0.25 volts. Okay, that's in the purple. Okay, Okay, we're going to add this up. Okay, we're going to multiply the top one by 2, and we're going to multiply the bottom one by 3. So how many electrons are being transferred in this reaction? This is a 6 electron transfer reaction. This is a 6 electron transfer reaction. Okay, we have 2 Cr solid goes to 2 Cr plus 3 aqueous plus 6 E minus. We have 6 E minus plus 3 nickel plus 2 goes to 3 nickel solid. All right, question, I multiply the top by 2. What is this voltage? Stays the same. Question, I multiply the bottom one by 3. What is this voltage? Stays the same. Okay, the difference now is I can now have calculated E cell, which is 0.74 minus 0.25, and what is that on our calculator? Is it positive 0.49? And this is my net reaction. It's the same actually, except I balanced it. So let's answer this question here. Calculating E cell, you're going to put positive 0.49 volts. Is this spontaneous? The answer is yes. Okay, why did I say it's spontaneous? Because we have a positive E cell. And then we got to put it in this notation. Okay, don't forget to do this. Okay, what is our anode couple? Okay, chromium. So it's going to be Cr solid. You're going to draw one straight line down, Cr plus 3 aqueous. Okay, what is our salt bridge? 2 lines, and now the cathode couple. The cathode couple here is Ni plus 2 aqueous. You can draw a straight line down, Ni solid. Okay, so this is the answer. It's spontaneous, positive 0.490 volt, positive 0.49 volts. And yeah, this is the galvanic cell notation. Yes, sir, go ahead.
So, back there, why did you multiply the top one by 2 and the bottom one by 3?
To cancel out the electrons.
Okay.
2 times 3 is 6, 3 times 2 is 6. Yeah, you can't, Lee, we cannot have any electrons anywhere here. Okay, they're really bad. Okay. They're also bad for health. They're also bad for, they call them free radicals. They're not good. Okay, so make sure, another important point, when you multiply this by 2 and the bottom by 3 to cancel out the electrons, this number still stays the same. All right, here's one more practice problem. I'm going to not put in the coefficients, because what we're doing is we're breaking this down and building it back up. So let's break this down. We'll first break this down to Al solid goes to Al plus 3. Okay, how many electrons and where do we put them to balance this out? Okay, I'm getting 3 electrons on the product side. And what is this on our calculator? What is this on our sheet? I'm sorry. It's not negative 1.66 volts. It is not. What is it going to be? It's going to be positive, right? Because we flip it. So positive 1.66 volts. Okay, we call this E anode. Okay, we have BE plus 2 goes to BE solid. How many electrons and where? 2 electrons on the reactant side. And what is beryllium plus 2E minus goes to beryllium solid? I see it right here. I'm getting negative 1.85 volts. This is the cathode. This looks a lot like our previous problem, because what do we need to do? We'll multiply the top part by 2, and we'll multiply the bottom part by 3. Okay, so how many electrons are getting transferred here? Okay, just like the previous problem, this is a 6 electron transfer reaction. Okay, we'll write it down. So our net reaction is, now you notice I'm going to regenerate this. We broke it down, we built it back up, but what's nice is now I got E cell, which is positive 1.66 minus 1.85, and that's minus 0.19 volts. All right, our net is 2Al solid plus 3Be plus 2 goes to 2Al plus 3 plus 3Be solid. And this is the answer. This is spontaneous or non-spontaneous? Okay, actually the flip would happen. Okay, the reverse will happen, but this way is not happening. And let's just do the anode and cathode couple, the notation. Anode couple, you're going to do Al, draw solid. We're going to draw one line, Al plus 3, aqueous. Okay, salt bridge, and then Be plus 2. We're going to draw one line, Be solid. So you can omit the coefficients, or you can keep them. I don't really. It's not a important issue for me. Okay, some people put two, and they'll put the 2s and the 3s in. I don't. It doesn't matter. Okay? I'm not going to make a big deal of it. All right. So yeah. Okay, this and this you should be able to go back and forth on the exam. Are there any questions or comments here? All right, let's go now to page 4 of our notes. The back side. Oh, I am so sorry about this. Actually, I have another copy. Can you get me another copy? Thank you, Bill. All right, let's go over page 4 and 5 here. So page 4 is here. All right, circle which one has the higher entropy. We went over this at the beginning of the class. Higher entropy, we're looking for a positive S or delta S. Okay, and entropy is disorder. All right, so which is more disorder? 1 mole of O2 gas or 1 mole of HNO3 aqueous? Gas or an aqueous? So gas spreads around, moves around. Aqueous is solute and solvent, so there's more stuff. But which is more disordered? Okay, it's going to be the gas. Okay, it's going to be the gas. Okay, the aqueous is a liquid, but it's not a pure liquid. It's solute plus solvent. But the gas is very, very disordered. Okay, there's gas molecules all around this room right now. HNO3 is just in its little beaker. 3 mole of N2 or 2 mole of N2. Okay, more gas, more collisions, more motion, that is more disorder. 1 mole of NaCl solid or 1 mole of NaCl aqueous, which do you think is more disordered? Okay, a solid is very ordered. NaCl in water, aqueous is more disordered. So this would have the higher entropy because it's more disordered. Milk at 25 degrees or milk at 37 degrees. Okay, higher temperature, more entropy. Okay, calcium phosphate solid or sodium chloride solid. They're both solids. So which would you guess would have the most entropy, most disorder? It will be the one that has more mass. So we usually associate more mass with more disorder. So that is how we tackle these types of problems here. All right, next up here is something called the Nernst equation. I'll give you this on the exam. Okay, and the Nernst equation is for calculating E cell, not E cell. Okay. What's the difference? Okay, this is standard state. This is non-standard state. So it could be any temperature, it could be any pressure if it's a gas, it could be any concentration if it's a solution. Okay, this is a very specific set. This is 1 atmospheric pressure if it's a gas, 25 degrees C temperature, and 1 molar for the solution. Okay, so this is called the standard state. But the Nernst equation is what this is called. Okay, it isn't about calculating E cell, okay, from standard state, calculating E cell from our table. Okay, it's about calculating E cell non-standard state and any type of condition, any type of temperature. All right, so let's go here. Okay, we have this galvanic cell notation here. And let's go ahead. It's the anode couple. What are those 2 lines called? Salt bridge. And then Sn plus 2 goes to Sn solid. So we're going to break this down. The anode couple first. We'll do this in blue ink. Okay, we have magnesium solid going to Mg plus 2. All right, how many electrons and where should it go? 2 electrons, and it should go in the product side. And what is the voltage associated with this? Okay, it's not negative 2.37, but positive. Okay, why is it positive? Because in this problem, we have to flip it. Okay, so this is positive 2.37 volts. And this is the anode. Okay, the cathode is going to be this. Okay, so we have Sn plus 2 going to Sn solid. Sn plus 2. How many electrons and where should we put them? Okay, we're going to put 2 electrons on the reactant side. And is this reduction or oxidation? Reduction, and reduction happens at the cathode. And what is the voltage with this? Let's look at our table. 0.1, negative 0.14. Yep, this is it. How many electrons are being transferred here? 2. This is a 2 electron transfer reaction. Alright, these 2 electrons will cancel. Alright, and we are left with Mg solid plus Sn plus 2 aqueous goes to Sn solid plus magnesium plus 2 aqueous. Aqueous means dissolved in water. Alright, doing all this, we have calculated an E cell, which is 2.37 minus a 0.14, right? And this is going to be positive 2.34 volts. Is that what you're getting? So this is not the answer, okay, because those are under standard state conditions. Okay, we are under the conditions of 2.24 molar Mg plus and 2.4 molar 10 times Sn plus 2. So we have our E cell here. Okay, what is N here? N is 2. This is a 2 electron transfer reaction. And then we need to calculate Q. Okay, Q is just like K. In fact, we use it to compare to K and its products over reactants. If Q is equal to K, we're in equilibrium. And then we don't put any solids in here or liquids. So Mg plus 2 concentration is going to be 0.24 molar. And then the Sn plus 2 concentration, 10. This is 10. Tin's concentration would be 2.4 molar. This Q has no units, and this is 0.1. Okay. All right, and now we have everything to plug it in, so this will be plug and play into the Nernst equation. So let's plug and play into the Nernst equation. E is equal to E cell, which is 2.23 volts minus 0.0257 volts divided by 2, natural log of Q, and we just calculated Q, products or reactants, as 0.1. Wait, can we do this on our calculator? What time is it? Right, let's see how we can do this on our calculator. Okay, first I would do natural log of 0.1. Okay, times a minus, this is important, times a minus 0.0257. Times negative 0.0257. Okay, we're going to divide this by 2. Divide by 2. Okay. Plus 2.23 volts. So I'm getting about positive 2.26 volts as my answer. Okay. Positive 2.26 volts. So 2.3 volt battery between magnesium and strontium 10. I'm sorry, this is 10. Okay, under these concentrations. All right, Again, Nernst equation. I'll give you this equation on the exam, so you do not have to memorize it. You just plug and play. All right, our final problem here is this one. I calculate delta G for the following reaction. And, I'll give you this equation. You should be able to choose which equation best fits. And let's go ahead and knock this one out. All right. So we have AU going to AU plus 3. So we'll write this down. All right, how many electrons and where should it go to balance this? All right, 3 electrons on the product side. And what is the voltage with this? Where are you? Are you even here?
Gold is up here. When it's basically like the AQ plus the electrons all solid, it's a positive 1.5. We have to flip it, so it's going to be negative 1.5.
Yes, I see it right now. Thank you, Billy. Okay, did you hear her? She was exactly correct. We need to flip it, and that's going to make it negative 1.54 volts. And this is the anode. And then let's do calcium going to calcium solid. Calcium plus 2 going to calcium solid. Alright, I am going to put 2 electrons on the reactant side to balance this. And what is this reduction voltage? This is at the bottom. I'm getting negative 2.87. Negative 2.87. Wow. This is definitely not going to work as a battery. Okay, so AU will not get oxidized by calcium. In fact, AU is all the way at the top of the chart, and calcium is all the way at the bottom of the chart. So anyways, this is a 6 electron transfer reaction. Okay. So negative 1.50 plus a negative 2.87. This is negative 4.37 volts. Crazy. Okay, it's negative 4 volts. And this is a 6 electron transfer reaction. We have 2 AU solid plus 3 calcium plus 2 aqueous goes to 2 AL plus AU plus 3 plus 3 calcium solid. Okay, so notice we regenerated the original problem, but now we've got E cell. And like we mentioned, this is a 6 electron transfer reaction. Alright, it's asking for delta G, and we can solve it for this. Okay, F is the Faraday constant, which is something I will give you. And we'll just plug and chug it, and we should be done. Okay, minus N. What is N here? 6F is the Faraday constant. E cell, we just calculated E cell as minus 4.37 volts. Volts cancel. And what is this on our calculator? Minus 6 times minus 4.37. 24 something. 26.22 times 96,500. I'm getting 200. Okay, you know what? I'm going to divide by 1,000. I'm getting about 2,530 kilojoules. 2,530 kilojoules. Yes, sorry about that. So after we plug and play it into this equation, this is the value I'm getting. I divided it by 1,000 to get it in kilojoules. Okay, but you can put it in joules also, that's fine. All right, couple of things, some wrap-up points. This is negative 4.37. This is what I'm going to call a dead battery, okay, for lack of a better term. This reaction, okay, it's not happening. Okay, what happens would be the flip. Okay, would be the flip. If we flip this reaction, that would be positive 4.37 volts. That would happen. And next thing is the positive 2530 kilojoules. Okay, what does the positive Gibbs free energy tell you? Endergonic. Okay, it's endergonic. So that also tells us this reaction favors the reactants. This reaction, non-spontaneous, favors the reactants, all the same thing. Okay. All right, let me check the time here. Okay, it's 10:34. All right, endergonic. Okay, notice how they corroborate each other. Favors reactants because it's a dead battery, favors reactants. Okay. All right, anode couple. AU solid, one line, AU plus 3. Cathode couple, Ca plus 2. One line down, Ca solid. Okay, this reaction is not favored. The flip reaction is favored. Okay, what's more favored is calcium being oxidized to calcium plus 2, Au plus 3 being reduced to Au. Okay, that's favored. Okay, the reverse, which is what we have shown here, is not favored. Okay, this is not favored. Why? Negative 4 volts, positive 2,000 kilojoules. Okay, not a reaction, non-spontaneous. All right, I am done with the test review. So if you have any questions, you can email me, but you can use this as a guide. You can watch the video, do your quiz, homeworks. Okay. I'll see you on Thursday. All right, have a good day. Turn in your stuff at 2 o'clock. I'll be in my office.